I recently flew from Milan to Dulles Airport in the United States on a Airbus 380. This airplane was a high-speed airplane near the speed of sound. And when you look at that airplane, like all commercial airlines today, they have swept wings, wings that sweep back instead of straight wings. If you look at all military, high-performance, high-speed military airplanes today, they all have swept wings. Well, where did that come from? Who had the idea? Who invented the idea of a swept wing for high-speed flight? That concept was generated through the genius of one man. His name was Adolf Bussmann in 1935, where he gave a paper in Rome, Italy, at a conference called the Volta Conference on high-speed aerodynamics. And he conceived the idea that for high-speed airplanes, and he was thinking about supersonic airplanes, that they ought to have swept wings. That idea was ignored by scientists, engineers from the U.S. and from England, but was latched onto by people in Germany. And within a year, Germany was doing a great deal of research work on the aerodynamics of swept wings. The independently and totally unaware of the German swept wing work, the concept of a swept wing was conceived by a famous aerodynamicist here in the United States by the name of Robert T. Jones, working for the National Advisory Committee for Aeronautics, NACA, which later on in 1958 morphed into NASA. And Jones conceived the idea that for efficient high-speed flight, airplanes should have swept wings. His idea didn't gain much interest in the U.S. until U.S. investigative teams went into Germany, discovered all this experimental work on swept wings, and suddenly put the two and two together and said, this must mean something. And so right after World War II, the development of swept wings ballooned into, for example, Boeing was designing a bomber called the B-47 with a straight wing. Suddenly, it came out with a swept wing. North American was designing a fighter airplane, the F-86, with a straight wing. Suddenly, it came out with a 35-degree swept wing. And the swept wing airplane was born. Therefore, the invention of the swept wing was really an idea that came from the minds of two people, independent people, without knowledge of what each one was doing. Adolf Bussmann in Germany in the 1930s and R.T. Jones in the United States beginning in 1944. And ultimately, the United States quickly picked up on this and designed swept-wing airplanes, jet-propelled airplanes, after World War II.
Before, during, and after World War II, there was a widespread perception that aeronautics faced a so-called sound barrier at speeds around 767 miles per hour, also known as Mach 1. There were at least three obstacles. First, it was common knowledge that lift started to decrease at very high subsonic Mach numbers, above about Mach 0.8. Second, at the same time, the drag started to increase substantially. And third, not only was it harder to stay aloft and move forward, there was also a significant loss of control that pilots encountered during high-speed test dives. For example, on November 4th, 1941, shortly before Pearl Harbor, Ralph Virden had conducted a high-speed dive in a Lockheed P-38, developed almost 4 years by one of the most famous aircraft designers of all time, Clarence Kelly Johnson. The plane shook, the controls locked up, and the tail suddenly ripped off, resulting in a fiery crash into a house in Glendale, California. And what made all this even more puzzling was that at flight speeds beyond the speed of sound, scientists knew from ballistic testing that the aerodynamic drag coefficient actually came back down as the Mach number continued to increase deeper into the supersonic regime. It was as if there was some kind of inherent physical limit, a literal sound barrier that prevented flight near or at the speed of sound. It seemed that supersonic flight was possible, but how to transition through what came to be called the transonic regime was a huge concern. If bullets could go faster than sound, why not airplanes? The breakthrough came when the National Advisory Committee for Aeronautics, or NACA, which was the predecessor to NASA, built special transonic wind tunnels to study the phenomena happening at transonic speeds. And what they found was startling. When the airspeed increased above a certain threshold, shock waves began to form on the wing. And as the velocity continued to increase, the strength of the shock increased and its location on the wing changed. They found that the location of the shock was very sensitive to parameters such as the flow velocity and the wing angle of attack. The implication of this was huge for flight approaching the speed of sound. The presence of the shock on the body would dramatically change the distribution of pressure on the wing. As the shock position moved further aft on the wing, which would happen at higher flight speeds, a region of low pressure also moved further and further aft on the wing. This aft loading of the airfoil changes the center of pressure on the upper surface. This change in location of the net force would, in turn, change the moment acting on the wing, making the wing more nose-heavy. At the same time, the presence of the shock would dramatically increase the drag. When the air flows across a shock, it experiences a very rapid increase in pressure. This is an adverse pressure gradient, which tends to cause the flow to separate. So with a shock present on the wings, boundary layer separation is much more likely to occur. Then, when the boundary layer separates, the wake thickens dramatically and pressure drag goes way up. This was one of the reasons why they saw a dramatic increase in drag the closer they got to the speed of sound. The negative consequences of shocks on the aircraft were later defined by the famed Theodore von Karman in his Messenger lecture at Cornell University in 1953. First, the appearance of a shock on the wing can lead to a sudden change in the trim of the aircraft, which forces it out of balance. Second, the presence of shocks on the control surfaces can make a dramatic increase in the force required on the stick to keep the aircraft under control. And the control surfaces can experience an uncommanded deflection, sending the aircraft out of control. And third, strong vibrations could be encountered as the shock bounces around on the aircraft's surface. All three of these critical features could be present at once. Imagine that you're the test pilot of an aircraft and advancing the throttle with trepidation to higher and higher Mach number. Suddenly, you encounter significant buffeting of the aircraft and lock of the control surfaces. Panic would set in. Since the scientific community at that time did not yet understand the physical causes of these events, compressibility effects were shrouded in great mystery. So it's no wonder that the community at large considered the speed of sound to be a barrier to high-speed flight. The loss of lift, the significant increase in drag, and the extremely hazardous impacts on aircraft stability and control were indeed dangerous and appeared unconquerable. Now, at a simple level, the speed of sound and how it's different from the speed of light is familiar from thunderstorms. If you see a flash of lightning and then count once per second until you hear the clap of thunder corresponding to the flash, you can tell how far away that particular lightning strike was. The general rule of thumb is 1 mile of separation will give a 5-second delay between the lightning strike and when we hear it. This rule of thumb states that sound travels 5,280 feet, or 1 mile, within 5 seconds. This gives the speed of sound of 1,056 feet per second, which is exactly what the speed of sound is on a very cold day with a temperature of 5 degrees Fahrenheit. On a 70-degree day, the speed of sound is a little faster at 1,128 feet per second, or 770 miles per hour. So the old rule of thumb is fairly accurate. Now let's think about how sound propagates through air. A pressure disturbance at a particular location is communicated to the surrounding air by intermolecular collisions. More frequent collisions lead to faster propagation of the sound wave. The most dominant factor for the rate of collisions is the temperature of the gas, which is a measure of the internal energy of the gas. The average molecular velocity, which dictates the frequency of collisions in a gas, depends on the square root of temperature. So the speed of sound also depends on the square root of absolute temperature. So as the atmosphere gets hotter, the speed of sound also increases slightly. The Mach number is simply the ratio of velocity to the local speed of sound. A Mach number of 1, a flight speed equal to the speed of sound, while any Mach number less than that is subsonic, and any value above 1 is supersonic. Besides being an indicator of the sonic condition, Mach number also tells us the relative importance of compressibility effects. At a Mach number below about 0.3, any compressibility effects are negligible, and engineers often assume that air density is constant. Between Mach 0.3 and about 0.8, compressibility effects become increasingly dominant and must be accounted for. Above about Mach 0.8, local shock waves are usually present, and the drag on a flight vehicle increases dramatically. From Mach 0.8 to about 1.2, this regime is referred to as the transonic regime, a phrase jointly coined by Theodore von Karman and Hugh Dryden. Compressibility effects and why shocks form can be visualized more easily by simplifying the situation to an acoustic point source that can move through the air. The point source radiates pulses of acoustic energy at equally spaced time intervals. If the acoustic source is not moving, then all of the disturbance waves propagate out radially and uniformly. Each radial location receives the sound wave at the same time. But if the sound source is moving, say at half the speed of sound, then the sound waves no longer radiate equally in all directions. The sound waves on the upstream side of the motion are bunched up with a spacing that is half of what it was in the quiescent case. You can think of it as the sound source chasing the sound wave that it just emitted, but is traveling only half as fast as the wave propagation speed. This is the same physical reason for the Doppler effect, where the frequency of an oncoming source of sound is shifted higher. If the sound source is moving with a speed equal to the speed of sound, it is no longer possible for sound energy to propagate upstream, since the sound source is moving at exactly the same speed as the wave propagation speed. Thus, no upstream position is aware of the sound source until the sound source is actually there. An upstream observer would not be able to detect the sound source until it arrived. We call this a zone of silence. Lastly, suppose the sound source is moving at a speed that is twice the speed of sound. Clearly, an adjacent observer cannot detect the sound source until well after its arrival. The zone of silence now extends to include a wider region around the source, where only positions within a small downstream cone can detect the presence of the source. For a speed of Mach 2, the half angle of this cone is only 30 degrees. As Theodore von Karman has quipped, nobody ever heard the bullet that killed him. Since a bullet travels at a speed well above the speed of sound, it would be impossible for someone to hear the gunshot before being struck by the bullet. For an aircraft in flight, it's helpful to think of the aircraft as pushing its way through the air, with the air molecules forced out of the way to accommodate the presence of the aircraft. But at speeds closer to the speed of sound, movement of the aircraft through the air produces disturbances, pressure waves, which propagate ahead of the aircraft and communicate to the upstream air molecules about the presence of the oncoming vehicle. This upstream propagation of information always occurs at the speed of sound. As the flight vehicle moves faster, with a speed that approaches the speed of sound, there is less time available for the upstream air molecules to respond to the pressure disturbances. Thus, the air molecules tend to compress, but they bunch up more than they would in an incompressible flow. So the density of air increases immediately in front of the aircraft. This compression of air results in greater deflection of the streamlines and a thickening of the effective wing shape. The effects of compressibility can be conveyed by a simple relationship that was independently derived in Germany and England, referred to as the Prandtl-Glauert compressibility correction. This rule predicts that there will be an increase in lift as the free stream Mach number increases, since the quantity in the denominator decreases as Mach number goes up. This rule is really an approximation, but it allows us to appreciate the impact of increasing flight Mach number. As the free stream Mach number increases, the upstream propagation of information is inhibited, since the aircraft's speed is approaching the speed of sound. The distance between successive pressure waves decreases, and the disturbances start to coalesce. And finally, when the flight vehicle reaches the speed of sound, it is no longer possible for the disturbance information to propagate upstream. These disturbances coalesce into a shock wave, which has a sudden change in physical properties. There is a nearly instantaneous jump in velocity, pressure, temperature, and density across a shock wave. It's interesting to note that shock waves can form on a vehicle well before the flight speed of the vehicle goes supersonic. This is because the local flow velocity around portions of the wing can be much higher than the free stream velocity, since the flow accelerates around the wing. In fact, it's very common for commercial airliners, which cruise at about Mach 0.82, to have shocks forming on the wings. This is a common feature of the transonic regime, the presence of local airflows greater than the speed of sound for an aircraft whose overall movement is less than the speed of sound. In fact, these shock waves can be visible to the passengers sitting near the wing. If the angle of the sun is just right, the density gradient across the shock will refract light by differing angles, and a shadow will be cast on the wing surface due to the presence of the shock. When an aircraft's flight speed exceeds the speed of sound, then a shock wave will form at the nose of the aircraft, and usually at other locations on the aircraft body. This shock wave can be visualized by the refraction of light through the density gradient resulting from the shock. The reason for the refraction of light across a shock is the exact same reason why we see a mirage over a roadway or a desert on a hot day. The hot air rising from these surfaces is much less dense than the surrounding air, and the light is refracted by a different amount. This effect, called the Schlieren technique, has enabled some interesting methods for visualizing the flow. In fact, the Schlieren technique was one of the key tools that NACA researchers used in the 1940s to develop an understanding of shocks and compressibility effects. Much more recently, NASA has developed a technique where a chase plane with a high-speed camera images light rays from a cluttered background that have passed through the flow field around an aircraft. Post-processing of these images to extract density gradients results in striking visualizations of the shock wave pattern around modern supersonic aircraft. We can see shock waves forming on the aircraft nose, at the engine inlets, at the wing body junctions, at the tail, and at the engine nozzle. And just a short distance away from the aircraft, we can also observe two separate shock waves merging into a single one. Farther away from the aircraft, this process continues until there are two predominant waves, one formed from the nose and the other from the tail. The combination of these two disturbances produces what is referred to as an N wave, so named due to the characteristic shape of its pressure time history. This N wave has two very strong pressure jumps that happen in a short amount of time as the aircraft flies above some object on the ground. This is exactly what a sonic boom is. Sometimes observers on the ground can even separately discern the two pressure jumps within a single N wave, leading to the characteristic double boom from the space shuttle on re-entry. After supersonic flight became possible in the 1940s, it quickly became apparent that this sonic boom could have very destructive consequences. One early example was a ceremonial flyover of a four-ship of F-105 Thunder Chief fighter aircraft over the U.S. Air Force Academy on May 31, 1968. Pilots of these commemoration flights like to push the boundaries, perhaps in an effort to one-up their colleagues, so there's a push to greater flight speeds on these low-level flyovers. Well, for this demonstration in 1968, the pilot came in a bit too low and a bit too fast. As the F-105 zoomed in, it cleared the buildings on campus by only about 50 feet, and then pulled up with full afterburner on. This maneuver caused the aircraft to momentarily exceed the speed of sound, causing a relatively strong sonic boom at low altitude. And the result was catastrophic. Over 300 windows at the Academy were broken, and at least 15 people were injured by flying shards of broken glass. The total repair bill was estimated at over $250,000 for this high-speed stunt. So, in order to prevent such incidents, as well as because of concerns about noise, the FAA instituted a ban in 1973 on supersonic flight of non-military aircraft over the continental United States. When the Concorde was flying, the pilots had to decelerate to subsonic speeds before they could fly over the U.S., limiting the high-speed flight only to regions over the ocean. NASA and industry have worked on concepts to reduce the strength of the sonic boom through shaping of the N-wave. The quiet supersonic technology X-plane demonstrator is shaped such that the magnitude of the overpressure generated by the N-wave is reduced and spread out over time, such that the shaped signature will be less like a boom and more like a soft thump. Let's now turn our attention back to the World War II era to discuss how aircraft design was radically changed in order to handle the effects of compressibility and shock waves. With propeller-driven aircraft going faster and faster, the first sign of compressibility effects and locally supersonic flow occurred on the propeller blades. Here, the rotational speed of the blade is combined with the forward flight speed of the aircraft to make for a very high Mach number, taking relative velocity at the blade tips well above the speed of sound. This results in significant drag, ultimately requiring much more torque to drive the propeller. So propellers were becoming a limiting factor in the quest to go fast. Fortuitously, the limitations of propellers coincided with the invention of the jet engine. Suddenly, aircraft designers could attain dramatic increases in maximum flight speeds, where the maximum speed jumped from 469 miles per hour with the propeller-driven Messerschmitt 209 in 1939 to 606 miles per hour with the jet-driven Gloster Meteor F Mark IV in 1945. For the next 31 years, the increases just kept coming. But the engine that set the stage for the first supersonic flight, known as breaking the sound barrier of roughly 770 miles per hour, was a rocket engine. On October 14, 1947, over Rogers Dry Lake Bed in the Mojave Desert, Chuck Yeager strapped into the Bell X-1 for that record attempt. The X-1, simply put, was a sleek rocket with wings that were solely designed for speed. Indeed, it was powered by a rocket engine with a fixed supply of fuel on board, and the inefficiency associated with rocket propulsion, flight for long periods could not be sustained. But it was long enough. A B-29 Superfortress carried the X-1 aloft to an altitude of 20,000 feet, where it was released from underneath the wing. After a momentary delay, Yeager fired the rocket motor and off he went. Anticipating the potential for loss of control, Yeager successively accelerated to a Mach number of 0.83, 0.88, and 0.92, gingerly testing the elevator at each condition, looking for any sign of control lockup or loss of control effectiveness that were so often encountered in that era. Finding no anomalies, he continued to push the Mach number even higher. While at an altitude of 42,000 feet, the Mach number pushed up to a value of 0.98, fluctuated momentarily, and then jumped to a value off the scale. Post-flight data analysis indicated that he had accelerated as fast as Mach 1.06. He had done it. In this moment, Yeager became the first human being to pilot a flight vehicle faster than the speed of sound, and he lived to tell about it. Suddenly, the idea of a sound barrier was not so threatening. Yeager's flight cleared the way for a continued push towards ever faster flight speeds in the quest for scientific understanding and higher performance flight. The flight Mach number where shocks initially appear at some point on the aircraft is called the critical condition. Aerodynamicists invest a lot of effort in pushing the critical Mach number as high as possible to enable the aircraft to fly even faster and delaying the onset of shocks and the associated drag rise. There are a number of techniques and tricks that aerodynamicists can use to push the critical Mach number higher, delaying the problems induced by compressibility effects. Before and during World War II, the Germans came across an interesting idea for reducing the wave drag on a high-speed aircraft using swept-back wings. This idea was first presented by Adolf Bussmann at the 1935 invitation-only Volta Conference. He proposed an idea stating that compressibility effects on a wing were due to the Mach number of the flow perpendicular to the leading edge. So if the wing were swept back, the component of flow velocity parallel to the leading edge would not have an impact, leaving only the component perpendicular to the leading edge to affect the wave drag. This allowed a designer to sweep the wings back and increase the flight Mach number at which shocks and other compressibility effects would be encountered. Interestingly, the American researchers who attended the conference didn't really pick up on the idea and promptly forgot about it. However, within Germany, the idea resonated and they ran with it. This led to a substantial investment of energy and research dollars to investigate the effects of swept wings on high-speed aerodynamics. It wasn't until the closing days of World War II that the Americans caught on to the idea. In an effort to capture as much German aerodynamic know-how as possible at the conclusion of the war, the US sent a delegation of top scientists and engineers to Germany, led by Theodor von Karman. One of their visits was to a German research shop at Braunschweig on May 7th, the day before VE Day. At Braunschweig, they stumbled upon reams of data and wind tunnel models that showed strong evidence of a sustained research program into high-speed flight. The effects of wing sweep were immediately apparent to the American visitors. One member of the team was George Schairer, an engineer from Boeing. Almost immediately after seeing the German data for the first time, he wrote a detailed letter back to his home office describing what he had seen. He breathlessly explained the concept of the swept wing in his letter, knowing that the B-47 bomber was an ongoing design project within the company that would immediately benefit from this idea. Boeing engineers then threw out their conceptual design of a straight-winged bomber and started over with the new swept-wing design. The B-47 then went on to become a highly successful jet bomber that served at the outset of the Cold War. One key aircraft that directly flowed from the B-47 was the ubiquitous B-52 bomber, which first flew in 1952 and was still flying well into the 21st century. In fact, the B-52 design is so enduring that it is projected to continue flying at least until 2044. Another key aircraft that directly descended from the B-47 is the 707, the Boeing company's very first commercial jet airliner. So the entire lineage of Boeing's commercial airliners with swept wings can trace their roots to the B-47 and ultimately to Adolf Bussmann's aerodynamic work for increasing the critical Mach number. The thickness of the wing is another key aspect of the wing design that has a huge impact on shock development and the critical Mach number. With all other factors being equal, a thicker wing will induce more curvature of the streamlines, which in turn accentuates the compressibility effects. A thick wing will have a lower critical Mach number, meaning that shocks will initially appear at lower flight speeds. So many of the earliest supersonic aircraft had extremely thin wings. For example, the wing on the F-104 Starfighter was so thin that the leading edge thickness was a razor-sharp fraction of a millimeter thick and had to be protected during ground handling, both for the aircraft and for the ground crew. The disadvantage of a thin wing, however, is that there is much less room available for storing fuel, lighting systems, instrumentation, and actuators for the control surfaces. So, an alternative to extremely thin wings was developed, the supercritical airfoil. This idea can also trace its lineage back to the German aerodynamicists in the 1940s, but is most popularly associated with a NASA researcher named Richard Wickham. The supercritical airfoil is an interesting design where the leading edge is an elliptical shape and the upper surface has a long and flat rooftop. This shape produces rapid acceleration, but then a long, sustained region of relatively constant pressure. The idea is to keep the peak pressure below the critical pressure such that the local velocity remains subsonic over most of the airfoil surface. By delaying shock development to higher free-stream Mach numbers, the supercritical airfoil incurs less drag at a particular flight condition. Supercritical airfoils are now widely used on most commercial airliners since they offer such strong drag benefits. It turns out that Wickham also played a pivotal role in the development of a key aircraft prototype. In the late 1940s, the U.S. Air Force determined that a new interceptor aircraft was required, with the capability to fly at supersonic speeds. Convair won the competition for the interceptor and developed the YF-102 for this purpose. However, when they started test flights of the aircraft, the transonic drag rise was much higher than anticipated. In fact, the aircraft could not even exceed the speed of sound, with a maximum Mach number of 0.98. This is where Whitcomb's ideas came into play. He had just put forward his concept for an area rule, which basically states that transonic drag can be minimized by avoiding discontinuities in the cross-sectional area of an aircraft. The idea is to keep the cross-sectional area as constant as possible along the length of the aircraft. The presence of the wings at mid-fuselage will obviously increase the cross-sectional area. The only way to minimize the cross-sectional area increase was to reduce the size of the fuselage in the vicinity of the wing. This led to the design of area-ruled fuselages, which took on a waist-like shape, not unlike a traditional Coke bottle. The outcome of this development for the YF-102 was a dramatic improvement in performance. The YF-102A, which employed the area-ruled fuselage, had a larger engine, could now achieve a maximum Mach number of 1.22. This development saved the design from the chopping block, and Convair went on to produce 1,000 F-102 Delta Daggers, thanks to Whitcomb's innovative idea. So with all of these advancements in aerodynamics, what is the maximum speed of an aircraft today? The well-known SR-71 Blackbird is the current record holder, with a maximum recorded speed of 2,193 miles per hour, set in 1976, a little over Mach 2.85. Unofficially, however, it is widely known that the aircraft can fly much faster. One Blackbird pilot reported going as fast as Mach 3.5 in order to evade a missile over Libya. The SR-71 illustrates very well how shock waves drive the design of high-speed flight vehicles in some interesting ways. Oblique shocks, or shock waves oriented at an angle with respect to the flow direction, are pinned to sharp edges. Oblique shocks have much less drag than bow shocks, which form a head of blunt surfaces, but they do induce increased aerodynamic heating. So drag reduction, at the expense of increased aerodynamic heating, is the main reason why supersonic aircraft have pointy noses and sharp spikes in front of the engines. On the SR-71, there is a long conical forebody on each engine, which is specifically designed for forming an oblique shock at the front. If the conical forebody were not present, then a bow shock would form, which would produce much higher drag. The angle of the oblique shock depends on the angle of the forebody and on the oncoming Mach number of the flow. Higher Mach numbers result in smaller shock wave angles. The optimum angle for the shock wave should be designed into the flight vehicle such that the drag is minimized and inlet conditions for the engine are optimized. But with an aircraft such as the SR-71, there are interesting challenges that arise when the aircraft traverses a large range of flight Mach numbers. The pointed forebody on each engine on the SR-71 actually moves in flight, adjusting with the flight Mach number in order to maintain optimal flow conditions for the engine. Despite the fact that the SR-71 was designed in the early 1960s, its 1976 speed record went unsurpassed for over 40 years. It was and is an incredibly advanced aircraft design. And bringing things full circle, the designer of the SR-71 was none other than Kelly Johnson, the very same designer of the P-38 Lightning that encountered such severe compressibility effects back in 1941. This is a testament to the incredible pace of innovation and also to the amazing talent of Johnson and his team at the Lockheed Skunk Works. It is truly remarkable how much that Kelly Johnson and the entire aeronautical community learned about compressibility effects in high-speed flight in the few intervening years between the start of World War II and the SR-71 design of the 1960s. So what factors limit the maximum speed of the SR-71 design? There are two significant limiting factors: materials and propulsion systems. Advanced materials are required that can withstand the high temperatures associated with aerothermodynamic heating at such high flight speeds. The stagnation temperature is incredibly high, forcing the SR-71 to rely on titanium and composite materials for maintaining a lightweight design and effective strength at high temperature. But even these advanced materials have limits on strength and heating. Traditional jet engine propulsion systems become less effective at high Mach numbers. But while Chuck Yeager used a rocket to overcome this problem, high-speed air-breathing propulsion systems are also possible, such as ramjets and scramjets. The main idea of a ramjet is to achieve compression of the air by relying on the high speed of the flight vehicle to provide the driving force for compression. A scramjet is based on the same idea, except the combustion process happens at supersonic speeds within the engine. Ramjet and scramjet concepts only work well at supersonic or hypersonic speeds, but are the most efficient concepts at high speed. So, the next world record for a piloted aircraft will likely rely on a scramjet engine.